The evolution and future of solar sails, from theoretical concept to interstellar propulsion. 1. Executive summary. Solar sail propulsion represents a transformative approach to space travel, offering long-duration thrust without the need for onboard propellant. By leveraging the momentum of photons, solar sails provide an elegant, efficient, and scalable means of transportation through the vacuum of space. This white paper traces the historical development of solar sail technology, explains the underlying physics and engineering challenges, evaluates current and future applications, and envisions long-term interstellar missions enabled by light sail technology. With emerging advancements in materials, AI-driven control systems, and laser-augmented propulsion, solar sails may become a cornerstone of human and robotic exploration across the solar system and beyond. 2. Historical and conceptual foundations. 2.1 Early theoretical roots. The concept of using light for propulsion dates to Johannes Kepler in the early 17th century, who theorized that the tails of comets were affected by a solar breeze. In the 19th century, James Clerk Maxwell's equations confirmed that light possesses momentum, laying the theoretical groundwork for radiation pressure as a physical force. 2.2 20th century visionaries. Konstantin Tsiolkovsky and Friedrich Zander were among the first to propose solar sailing as a means of space propulsion in the early 1900s. These concepts, though highly visionary at the time, inspired subsequent generations of engineers and scientists to consider non-chemical propulsion methods. Science fiction writers like Arthur C. Clarke and Carl Sagan popularized the concept in the public imagination. 2.3 Transition to practice. In the late 20th century, space agencies began taking solar sails seriously. NASA, the Soviet space program, and later the Japanese space agency JAXA explored prototypes. The launch of Icaros in 2010 by JAXA marked the first successful solar sail flight, achieving interplanetary travel using radiation pressure. LightSail 1 and 2 by the Planetary Society further demonstrated practical orbit adjustments using photon momentum. 3. Physics of solar sail propulsion. 3.1 Photon momentum transfer. Photons, though massless, carry momentum given by, where is energy and is the speed of light. When a photon reflects off a surface, it imparts twice its momentum. The resulting force is given by where equals force equals solar power per unit area, solar flux equals sail area equals reflectivity coefficient equals speed of light. Over time, the continuous application of this small force results in significant velocity increases, particularly in deep space where gravitational drag is minimal. 3.2 Relativistic effects. At relativistic speeds, Doppler shifting reduces incoming photon energy, diminishing propulsion efficiency. Relativistic thermal management becomes crucial, as the absorbed energy must be radiated effectively to prevent sail degradation. 4. Engineering materials and deployment. 4.1 Sail materials. Solar sail materials must be ultra-lightweight, highly reflective, and resistant to radiation. Common materials include mylar, polyethylene terephthalate film, coated with aluminum. Kapton, polyimide film with high thermal resistance. Aluminized PET, offers a balance of strength, weight, and reflectivity. Metamaterials, engineered for wavelength-specific reflection and structural integrity. Key performance factors. Aerial density, targeting. Tensile strength, withstands deployment stresses. Degradation resistance, UV, ionizing radiation, micrometeoroids. 4.2 Structural and deployment engineering. Deployment strategies include boom deployment, extendable masts unfurl the sail. Spin deployment, centripetal force aids in unfolding. Inflatable ribs, pressurized tubes provide structure. Deployment must be autonomous, fault-tolerant, and minimally mechanical to reduce mass and failure points. 4.3 Thermal control. Sails absorb solar energy, risking overheating. Passive radiative cooling is preferred. Coatings may include high emissivity layers on the non-sun-facing side. Selective absorption filters to manage heat load. 5. Control, navigation, and stability. 5.1 Attitude control mechanisms. Maintaining and adjusting orientation is critical for trajectory control. Methods include tip vanes, small, movable surfaces that shift sail orientation. Magnetic torquers, interact with planetary magnetic fields, low Earth orbits. Electrochromic panels, alter reflectivity to shift force balance. 5.2 Precision navigation. Solar sails require fine navigation to maintain orbits and trajectory over long durations. AI systems must manage sun angle optimization, real-time course correction, integration with optical and pulsar-based navigation systems. 6. Laser-pushed light sails. 6.1 Ground-based laser arrays. High-power lasers offer an alternative to solar photons for propulsion. Arrays must overcome atmospheric distortion, beam divergence, power supply and waste heat management, target power density, for interstellar missions. 6.2 Orbital and lunar laser stations. Lunar-based lasers eliminate atmospheric issues and allow continuous beaming. They can be solar-powered and directed via adaptive optics. 6.3 Breakthrough Starshot case study. Proposes accelerating gram-scale sails to 20% light speed using multi-gigawatt ground-based lasers. Key design specs. Sail mass, 1 g. Area, 4 m². Acceleration, 60,000 g. Travel time to Proxima Centauri, 20 years. Challenges. Sail material survivability. Aiming precision. Communication back to Earth. 7. Mission architectures and use cases. 7.1 Near-term. Attitude control for smallsats. Deep space probes, Jupiter and beyond. Asteroid belt mapping. 7.2 Medium-term. Mars cargo transport. Solar system Internet nodes. Autonomous AI scout fleets. 7.3 Long-term. Interstellar microprobes. Terraforming seeders. Extragalactic communications relays. 8. Risks, failure modes, and redundancy. Potential threats include micrometeoroid impacts, radiation degradation, loss of control authority, redundancy strategies, multi-layer sails, modular sail networks, self-healing materials, future tech. 9. Philosophical and ethical considerations. Autonomous AI probes may precede human explorers. Key questions. What rights do AI systems have? Is panspermia ethical? How do we define exploration in a post-human context? These questions are central to the future role of humanity in a universe explored by intelligent machines we create. 10. Conclusion. Solar sails offer a new paradigm for space travel, silent, persistent, and scalable. From Kepler's early speculation to breakthrough starshot, the journey of solar sails is one of vision and perseverance. As we stand at the threshold of interstellar capability, solar sail technology may carry our dreams, machines, and messages across the cosmos, not with fire, but with light.